Welcome back to Math 332. In this video, we are going to look at one of the application of the process of diagonalizations. We have seen how we use the process of diagonalizations to solve a system of differential equations. And in this case, we are going to look at how we apply the process of diagonalizations through the computation of eigenvalues and eigenvectors to solve something that we call a recursive relations, or sometimes called the difference equations, which is equation that is in this form, which basically tells you the relationship between the t plus 1 terms in relationship to the t terms and the t minus 1 terms. We are going to use the methods of eigenvalue and eigenvectors, and through the process of diagonalizations, try to obtain something that we call the closed solutions, which is we want to find xt that only depends on t rather than all the previous terms or the previous terms. And in order to do that, we will have to first put this whole thing into a matrix form. And the way that we do it is going to be this. It's going to be weird if this is the first time you see it. But what happened is that there's actually only one kind of useful equation here, which is the xt plus 1, which is 6 times of xt minus 5 times of xt minus 1, which is our equation star right here. But in order to create a 2x2 matrix, we have to put in some redundant information such that like the xt terms here is equals to xt terms. So second row basically tells you that xt terms is equal to xt terms, and the first row tells you the xt plus 1 is equal to 6 times of this and minus 5 times of this. Okay, so this is what we call the equation double star. And let us introduce some notations. So suppose I call this column vectors ut plus 1. So the t plus 1 here will identify with this t plus 1. So if this is switched to t, then this is xt, and this is one term less than it, which is xt minus 1. So by using these two notations, the equation double star here basically can be rewritten as ut plus 1 equals to the matrix A. This is a matrix A times ut. So this whole system's equation double star is going to be reduced to these equations. So this is a 2x1 column vectors, 2x1 column vectors, and this is a 2x2 matrix. Okay, so this is how we code the difference equation or the recursive relations into a matrix form. And so let's look at some what happens if we try to compute ut plus 1. So ut plus 1 is equals to a times ut. This is the ut, and because of that, u1 is x1 and x0. And we have that information, which is 4, 0. We have that in the beginning, which is right here. We are given x0 equal to 0 and x1 equals to 4. So then we can play around with this recursive relation. So for example, at t equal to 1, we have u t equal to 1. So look at this equation here. If your t is equal to 1, then we have u2 is equals to au1. T equal to 2, we have u3 is equals to au2. And we know what au2 is. au2 is right here. So you can substitute au2 with au1. And then because a and a, you can multiply them together and have a squared u1. So the next terms is going to be like u4. u4 is going to be au3. And we know au3 from before. So we can substitute u3. And u3 is a squared u1. And you multiply them together and get a cubed u1. So you can do that so on and so forth. So you can get a formula which is ut plus 1 is equals to a to the power of t u1. So A is this matrix 6, 1, negative 5, 0. So AT is going to be this. The problem is that multiplying AT multiple times like that by itself is not something that's easy to compute. So even though we know that UT plus 1 is equal to AT multiplies U1, but the complications, direct computation of AT is going to be a little bit more problematic. So this is where the diagonalization process come in. So instead of doing it this way, we are going to rewrite our A as something else. So we don't want to use A. We want to use something that is related to A, but something that will help us in the computations. So to do that, we will have to do repeat the diagonalization process, and hopefully that will help. So we don't know how it will help, but let's just give it a shot and try to solve the eigenvalues problem and try to see whether or not we can diagonalize that matrix A. So in order to diagonalize matrix A, we need to find the matrix P, which consists of the columns. The columns of matrix P consist of the eigenvectors. So we have to find the eigenvectors, and in order to find the eigenvectors, we have to find the eigenvalue. So we have to first start with solving the eigenvalue problem. So we set the determinant of A minus lambda I equal to 0. You do that computations because it's 2 by by 2 is pretty easy to do that. And you can see that you have two eigenvalues, they are distinct, which is lambda equal to 1 and lambda equal to 5. You have 2 by 2 matrix and you have two distinct eigenvalue. So we know for sure this matrix A is diagonalizable. So you once you have the eigenvalues, you try to solve the eigenvectors problems. The eigenvectors, there are infinitely many of them. In fact, the eigenspace correspond to this eigenvalue lambda equal to 1 is the has dimension 1 and is spanned by these vectors 1, 1. But we don't have to take all the infinitely many eigenvectors. We just have to pick one. So let's just pick the basis 1, 1. And let's repeat this process for lambda equal to 5. Go through this process again. You will find the eigenspace for lambda equals to 5 is actually spanned by these vectors 5, 1. We can pick 5, 1 as the corresponding eigenvectors. Then we construct the matrix P. So the columns of P will consist of these eigenvectors. So 1, 1 coming from here, and then 5, 1 is coming from here. So if you do that, we talk about that in class, that once you constructed your P this way, your P inverse AP will equals to a diagonal matrix where the entries here will correspond to the eigenvalues for these eigenvectors. And the entries here will correspond to the eigenvectors. This eigenvalue will correspond to this eigenvectors 5, 1. So we have P inverse AP equals to D. When you have a relationship like that, we also say that A and D are similar matrix. A is similar to a diagonal matrix 1, 5. So we can rewrite this as A equals to PD P inverse. Let's just move things around. You get that. And back to our original equations. So our original equation is ut plus 1 equals to A and then ut. But then our A now is PD P inverse. So we're not working with A anymore. Our A can be successfully written as a product of 3 matrices, which is P and then D and then P inverse. And that is an advantage of writing it like this, because now you can see that instead of writing A, if we write it as PD P inverse, then we do these substitutions, t equal to 1, for example, then we have u2 equals to PDP inverse u1, and u3 will be PDP inverse u2, but then we know what happened to u2, so we substitute u2 as PDP inverse u1, and you can see that matrix multiplication is associative, so P inverse and P can be grouped together, and they kind of cancel each other out and give you the identity matrix, and identity matrix is basically like a 1, so once you multiply D, it would just be D, so then the D and the D itself can combine together, and that will give us D squared. So in fact, U3 is PD squared P inverse U1. So go through this process again. So what happened is U4. So U4 will be PDP inverse U3. Again, we already know U3 is this. So do these substitutions. PP inverse cancel each other out. D squared and D multiplied together get you D cubed. So it's exactly the same. So here right now, we have UT plus 1 is P, DT, P inverse U1. You can look at the index. So here, if this is 2, this is power 1, 3, this is power 2, 4, this is power 3. So therefore, T plus 1 will correspond to the power t. Now, the benefits of writing this is that we do know what d to the power of t is. So if you have a diagonal matrix and you multiply this diagonal matrix by itself multiple times, we know the result is pretty straightforward. You can do that computation. So d to the power of t, if your d is diagonal matrix, then what happens is everything is still a diagonal matrix. Everything off diagonal is still 0, and the diagonal entries will raise to the power of t. So we know that dt is this. Okay, so that's our dt. And once we have that, we can kind of go back to this equation and try to simplify it and extract all the necessary information. Okay, so the way we do it is this. So back to these equations, ut plus 1 is p dt p inverse u1. And so remember that our P consists of the column vectors V1 and V2. This is how our DT looks like. So the only thing that we don't really know is P inverse U1. Now, P inverse is a 2 by 2 matrix. U1 is a 2 by 1 matrix. So altogether, this is going to give you a 2 by 1 column vectors. And we actually know what the value of this. So we can compute this pretty easily because we know what U1 is. So let's just call this for... At this moment, let's just call the P inverse U1 as a C1, C2. We can find C1, C2 easily. Let's do that. So P is this matrix. P inverse is very easy to compute because it's 2 by 2. We can use these formulas to find P inverse. Apparently, this is our P inverse. So P inverse U1, that is your P inverse, and U1 is 4, 0, because recall that your U1 is X1 and X0, and that's our 4, 0. This is given. So if you do these computations, you will see that your P inverse U1 is nothing but -1 and 1. So that's our C1, that's our C2. Now, so we are almost done. Just look at the UT plus 1 equation. So there's a P, that's a D, and then this is P inverse U1, which is just these two numbers. Suppose let's just call them C1 and C2 for this at this moment. Just call them C1 and C2. And you can see that if you concentrate on the matrix multiplication here, so you multiply this with this with this, so it's just basically just this, and then multiply this with this and this with this. So this whole thing here is just C1 times 1 to the power of t, C2 times 5 to the power of t. So this is what happens if you multiply these two matrices together. So now you have this. And we have seen this many times before. If you have a matrix P and multiply with this, so if you do go through this multiplication, you will see that what happens is that this number here is kind of like a constant. This thing here will go in front of the vectors V1. These things here will go in front of the vectors V2. So we have numbers. This is also a numbers, and then you have the column vectors here, column vectors here. This is kind of like multiplying this matrix with two numbers. Okay, so these two numbers will go to the front as coefficient of V1, and the other numbers will go into the front as coefficient of V2. Right, so you should be able to see that pretty easily. So let's recall that what is UT plus 1? UT plus 1 is XT plus 1 and XT. So from here, you look at the second row, that is what we want. We want XT, isn't it? So our XT is actually equals to 5t and then minus 1. 1 to the power of t is always 1. So if you look at the second row of these equations, you will see that xt is 5t minus 1. And this is what we want to find. This is the so-called closed form solutions for these difference equations. And we can double check whether or not it fits the observations. So for example, we are given x0 is 0, x1 equal to 4. And if we use a recursive relationship, which is here, you can compute x2. x2 is 6, x1 minus 5, x0. Put in the number, you get 24. You can compute x3. Okay, so x3, according to these recursive relations, then you will have 6x2 minus 5x1. We know x2 from these computations, 24. We know x1 from here, so you do that computation is 124, so on and so forth. So these so-called closed form equations will also match those data. For example, when x equal to 0, 5 to the power of 0 is 1, 1 minus 1 is 0, that's x0. x1 will be 5 minus 1, which is 4. x2 will be 25 minus 1, which is 24. x3 will be 5 to the power of 3 minus 1, which is 125 minus 1, which is 124. So you see that these formulas x3 will generate what you get from playing around with the recursive relation. So this is called the closed form of the recursive relation. So this is a closed form solutions, and we can do it pretty easily by diagonalize the matrix and compute everything basically from these equations. So this is one application of why you want to do that using the diagonalized form of matrix A. So this is problematic. It's very difficult to compute what happened in general when you raise a non-diagonal matrix to any power. But if you can do this, you can see that AT is very difficult to compute, but DT is pretty easy to compute. And that's another applications of the process of diagonalizations, because diagonal matrix do enjoy this kind of special property. And hopefully with this, you should be able to do the homework problems. And also please check your indexes. The example that I gave, I think I screw up the index for this kind of recursive relation, but so you can forget about the notes and you can just concentrate on what you see in this video. And see you on Thursday.